started. You can get your homework out if you want. But so to a buffered solution, what works great for a buffered solution is you have in your water, you have your acid-base pair, just like you guys have been identifying. The first one, to me, is the easiest way, okay, this way. And you guys did a homework where basically what's easiest is if you have a weak acid and you put the salt, which is basically the conjugate base of the weak acid, or if you have a weak base and you put the salt, which is the conjugate acid, you kind of do it that way. Okay, but I guess one thing I'll put up on the board again is if you have a buffered solution where you have a conjugate acid-base pair that's in the liquid running around, you can get the pH of that buffered solution by taking the pKa, okay, that's from a table, plus log base 10 of the ratio, and you can either go molar concentration or moles. And it's always base, conjugate base, over conjugate acid. Okay, this is for buffered solutions. This is the HH equation, Henderson-Hasselbalch equation. Okay. So another way to get your acid-base pair in there is this way. And it's a little more involved. But I made a slide to kind of go along with this. Basically, you're going to start out with either your weak acid or your weak base, okay? And you are going to add to it a strong base or a strong acid, okay, to prepare the conjugate. So in this case, we could prepare the conjugate base. In this case, we would prepare the conjugate acid. I don't know if that makes sense. Notice I have a one-way arrow, and I have strong acid or strong base. Okay, so maybe that will suffice. So we did this problem. I'm not going to do it again because we did it on Monday. But this was the first way where it's easy. You just basically, you already had the, hopefully you guys are kind of getting under this scheme of things where if you see something like that, doesn't it look like a weak acid? Kicks off that proton. And if you see something like this, notice basically that is, you kick off the Na plus and you end up with a CH3COO minus. Okay, that is the conjugate acid-base pair that you have in that solution. So that was pretty kind of straightforward. And a lot of the homework, most of the problems that are going to be doing for Friday do this. Okay, I was thinking that they did the other, but they do this. But the other type of problem, here's an example of that. Okay, okay, let's see. Now, HCl, all sorts of bells and whistles should be going off for y'all. HCl is a strong acid. So guess what? This right down here is what we got going on here. Basically, to me, it's a little bit of chemistry on the front end to prepare your conjugate acid-base pairs. So here in a minute, you're going to see HCl will react with ammonia, NH3. I hope we're okay. Does that seem like it accept a proton? So actually, that's one of your weak bases. You'd find a Kb value for that. Okay, and so actually HCl here, your strong acid, is going to be your limited reactant. Limited reactant. It's all going to use up. Okay, so that, let's see, they don't give the volume, okay? They give the molarity of the strong acid, okay? They give the volume of the weak base, right? And they give the target pH, that 9.50, that's our target pH. So that's kind of what we have going on here. So to work this sort of problem, you need to recognize, like I said, that your weak base, your NH3, is going to be reacting with your strong acid with a one-way arrow. Weak base, strong acid, one-way arrow. And hopefully you kind of see what's being created over here. Okay, basically you have your NH4 plus. That is your conjugate acid of that weak base being NH3. So that's the chemistry on the front end to make your buffered solution. All right, so it becomes kind of a bean keeper, counting beans, bean counter. So ultimately, we need to come up with something to plug in our Henderson-Hasselbalch equation. Remember, another form of the Henderson-Hasselbalch equation is instead of molar concentrations of base to acid, you have moles. So pH is equal to pKa plus log base 10 of the number of moles of base, the number of moles of acid. One of the things students get mixed up, though, is the acid here in your HH equation is not HCl. It's that NH4+. Okay, so in this problem, your acid is NH4+, and your base is NH3. Okay. So, one of the things, we'll go ahead and knock it out now. One of the things is we're going to need the pKa of NH4+. If you try to find a Ka of NH4+, you're not going to find it. You're going to find the Kb of NH3. Okay? So this is one of those deals, and we've kind of talked about this before. To get to the Ka that you need to plug in to get the pKa for your HH equation, you're going to have to recognize it has this relationship with the Kb. Ka is equal to Kw divided by Kb. So in this case, of course, Kw with 2 sig figs is 1.0 times 10 to the minus 14 divided by Kb, which you do find on a table for ammonia, 1.8 times 10 to the minus 5th. Okay, so our Ka for ammonium is 5.6 times 10 to the minus 10th. And I'll go ahead and kind of reiterate what we're going to do basically is this is the one that we're going to go ahead and get the pKa of and plug into our HH equation. That's kind of why that's been done. So kind of back to the chemistry. Well, I guess not back to the chemistry. So this then is what we're going to plug into our pKa expression. This, not pKa expression, our HH expression. So that is 9.26, right? So remember that in order to see if your acid-base, conjugate acid-base pair that you've picked to be a buffered solution is good for the target pH, you look at the pKa. And so the pKa 9.26, not bad for a target buffered solution of 9.50. All right, so there's your HH equation. Okay. And remember, instead of the molar concentration, we can go with number of moles, whichever is best for your problem. And you're the one to decide what's best for your problem. In this case, actually, the moles is the best for us. The other thing is, remember, it's not a separate form of the HH equation. Well, I guess it kind of is. But we can solve this and get the relative number of moles of base divided by moles of acid is equal to 10 raised to the pH minus pKa power. And actually, do you see why that makes sense? Because do we know our target pH? Yep, 9.50. Do we know our pKa? Yep, 9.26. So things are kind of falling into place a little bit. Okay. All right. But remember, the subscript acid is not your strong acid. It's your conjugate acid that's created from your weak base. All right, so here's what's going to happen with the chemistry then. Can you see where basically we are going to convert some of our ammonia? Some of our NH3 is going to be totally one-way converted to NH4+. So the moles of NH3 we start with, we're going to end up with less moles of NH3 because they're converted to its conjugate, NH4+. Okay. Some of the NH3 will be reacted to form NH4+. The other thing is Another reason that we're going with moles instead of molarity is that as we add the strong acid, the HCl, as we add HCl to go ahead and convert some of our weak base into its conjugate weak acid, we're going to be increasing the soup, the liquid of our solution. Okay, so actually our molarity will be changing, but the moles will be easier to count. Okay, so we can count moles easier than we can count molarity. So thus we're going with the N, the moles instead of molarity. So let's see what we got. Like I said, in this sort of problem, whether it's, like in this case, a strong acid that's converting some of your weak base to its conjugate acid, or if you have a strong base that's converting some of a weak acid to its conjugate base, okay, the strong acid or strong base is in limited supply. So bottom line, we're going to use general chemistry 1 techniques to come up with the moles of NH3, okay, that are consumed, must be consumed, and then we'll subtract what's consumed from what we started with to get the amount remaining. And NH4 formed actually will be the same as NH3 consumed because the stoichiometry is a 1-to-1. Now this one I don't go with an ice table just because it doesn't make as much sense to me. Okay. We're going to stick with millimoles instead of all-out moles because then we don't have to worry about the whole milliliter to liter sort of thing. So whenever you're given molarity, which we're going to have to be dealing with, then we know that means moles of solute per liter of solution, or millimoles of solute per milliliter of solution. So we're going to stick with millimoles. So with that in mind, if you go back to your original problem, it said that you had 150 milliliters originally of your ammonia solution. It gave its molarity as 0.123 molar. So that means that there's 0.123 millimoles of ammonia in 1 milliliter of solution. So rounding to 3 sig figs, the millimoles of ammonia we start out with is 18.5. 18.5 millimoles of ammonia starting out. So again, that's what we have to go ahead and now react with our HCl. So to get the amount of that that's converted, we need to look to our limited supply reactant, which is the HCl. Okay. And remember what we're solving for is what volume of HCl do we need to add in order to get our target pH. So if we let X be equal to the millimoles of HCl we're going to add, then X will also be equal to the millimoles of NH3 that react, and will also be equal to the millimoles of NH4 plus that are formed. And that goes back to, remember that one-way arrow, that goes back to this one. NH3 plus, that's your weak base, plus your strong acid. One-way arrow forms your NH4 Cl, but the thing here is your ammonium cation. So if we let this be equal to minus, let's see, how do I say that? Well, this is the amount of this, that's reacting, and this will be the amount of that that's also formed, because the stoichiometry is 1-to-1. Okay, so when the dust finally settles, your limited reactant will be used up. No more HCl left. That's kind of the point of it. The millimoles of your NH3 that remain will be what you started with, 18.5 minus X. It looks like it should be an ice table, but I still don't think it's an ice table. And then, of course, the amount of NH4 plus form will be equal to X. So honestly, do you guys see where instead of using, this is why I don't think it's an ice table, because it's not an equilibrium constant expression, we are going to plug these values back into our HH expression, where this is the moles of base, and this is the moles of acid. back into the HX expression. So here's what that looks like. Okay, is your Henderson-Hasselbalch equation for buffered solutions. The moles of base is that 18.5 minus X. The moles of its conjugate acid is X, that's the NH4 plus, is equal to 10 raised to the pH minus the pKa. So 10 raised to the 9.50, your target pH, minus 9.26, the pKa of ammonium. So now I don't have the kind of, I only go to the answer. So there are a few steps, like algebraically, between, from between this and this, but it's not too bad. It's just algebra. I would take 10 raised to that quantity, and then I would kind of crisscross and make, take that times X is equal to 18.5 minus X. I would gather my X terms. But rounding to three significant figures, that's the millimoles of HCl you need. Oh, sorry. Well, kind of. That's the millimoles of NH4 plus that are produced. But also, if you look back a few slides, that's also the millimoles of HCl that you need, because the stoichiometry is 1-to-1. Okay, so that's what we need in HCl. Then we kind of go back to Gen Chem 1 stuff. We were given the molarity, and we have millimoles, and now we need to get to volume. So the molarity was 0.0883, so that means there's 0.0883 millimoles of HCl in 1 milliliter. Millimoles will cancel. We'd be left with milliliters of solution. So 76.5 milliliters of HCl solution is your answer, given that molarity, that target pH. It's a very practical sort of problem, potentially. So that was the second way to get your conjugate acid-base pair. What's the next slide? Okay. So we'll take a look at these. Like I was telling Chelsea, we kind of need to kind of keep moving. We got it. Tomorrow's experiment is titled a titration, right? We haven't talked about titrations yet. In the context of Gen Chem 2, we talked about them in Gen Chem 1, strong acid, strong base. So let's take a look at these. Before we take a look at these, I will tell you that all but 26, I'll just circle 26, and this is the only one where basically I'll say second method. Oops, second method. Really? SEC. Method of preparing buffer solution. The other ones actually, it's kind of back to the chemistry we talked about on Monday. So this is what they look like. Part 5B. So here's the first one. It gives you, it looks like the conjugate acid-base pairs. Just looking at the problem is NH3 and NH4 plus. Notice it gives you the molar concentration of NH4 plus, and it gives you the target pH. You're definitely going to use the Henderson-Hasselbalch equation. And I went ahead and rearranged it for its alternate form. Should be okay. The only catch here, and I think the only catch here I put with a green asterisk. Okay, so your conjugate acid is NH4 plus. You will not find NH4 plus on a table. You will find NH3 on a table for a weak base. So to get to that pKa of NH4 plus, you need to get it from the Kb of NH3. And then I kind of reminded you kind of how we did it before. The next one looks like this. Again, Henderson-Hasselbalch equation. You're supposed to come up with the pH. Those are easier, I think. And notice they give you the molarity of the weak acid, and they give you the molarity of the weak base. That one's not too bad. Okay, so A is pretty straightforward. The only catch with B, I went ahead and kind of gave you a heads up again. With B, you're dealing with ammonia and ammonium. So actually, if you did 8, you already have the pKa of NH4+, don't you? So you should be okay. But if you didn't have it, you'd have to go through this, through the Kb. Next one, use the Henderson-Hasselbalch equation. Okay, the target pH is given, and you can get the molarity of the weak base from mass and volume. The molarity of the weak acid is given, and you're supposed to knock out the pKa. Or look it up on the internet. For this one, yeah, you're given a series of solutions, and basically they say, would these make good buffered solutions? So in blue there, I said, if it's a buffered solution, the ones we're talking about, look for the conjugate acid-base pair. And so kind of in red, I circled clearly conjugate acid-base pairs. They look like they differ by a proton, and that's sweet. That's great. But then in green, like we were talking most recently, or you can get your conjugate acid-base pairs if you react a strong acid like HCl and D and E. If you react a strong acid with a weak base. And so to me, those kind of look like good candidates. So I don't want to do your homework, but that's kind of how I would look at it. For 14, you're after pH using of a buffered solution, so you use the Henderson-Hasselbalch equation. This is another one, kind of in orange there. I say you're dealing with something that you'll be given the Kb of the C6H5NH2. That Kb is on the table. So you need to get the Ka for C6H5NH3 using the method we looked at before. And then otherwise, it's not too bad. This one, prepare a buffered solution by dissolving a certain mass of benzoic acid in sodium benzoate. So there's your conjugate acid-base pairs. It gives the volume. I would use this one where you're dealing with moles instead of molarity. So I think you should be fine there. And the last one, the second part here is, says, all right, based upon what you came up with A, what if you want to take that solution you talked about in A, and what if you want to get it to a target pH of 4.00? And I looked in my notes to make sure which direction this would go. And you'll see that actually to go to 4.00, you need to make it more acidic. So actually, from A, you're going to come up with a pH that's more basic than 4.00. So that's my hint. For any of these, especially for 26, you know, if you get bogged down, if you like do all them and then you get to like whatever that was, 18 and then 26, and you start to get bogged down, well then just call it a day and hand in what you got. These do get harder. In fact, for this problem, 26, I actually said do this one for sure, do A for sure. A is not bad. This is the only one that actually does the second type of getting an acid base, of getting a buffered solution. So notice they said that you are going to add HCl to a sodium acetate solution. Acetate is a weak base, so basically what you're going to do is protonate a certain amount of that to make, you'll have acetate and acetic acid in your buffered solution. That reaction is shown up at the front. So the H3O plus is the same thing as H plus, and it's coming from your strong acid. So notice that you can actually, you're given millimoles of HCl because you have volume and molarity, or moles, not milliliters. So you're given moles of that limited reactant. So kind of like we talked about with this problem this afternoon, okay, you are going to get the moles of acid formed from basically your limited reactant, which is your HCl. You're going to have some of your base left, and you'll get that by difference. What you started with minus what reacted from your HCl. So those will plug into there. Of course, you can get your Ka for your acetic acid is on a table, so you can knock out the pKa and come up with the pH. So A is pretty straightforward. I put a little star, I put a little this one for sure with a smiley face. I'm going to kind of talk you through the rest of the problem. It feels like it starts to get bogged down. Actually, I'm only going to talk you through B because that's I ran out of energy. So B says, all right, so you have that solution A, which is awesome. Go ahead now and add it with a dose of a strong base. Barium hydroxide is a strong base. My hint there, and I look back at my notes to make sure this is right, all that is that barium hydroxide is going to react 1-to-1 and gobble up some of your strong acid. That's all it is. How much will it gobble up and will it run out? Yeah, your barium hydroxide will run out. You'll be left with some of your strong acid left. And then that's going to be what goes ahead and creates your buffered solution. So it's a good one. And then it kind of goes downhill from there. Okay? So if you can do A and B, I'd give you a total smiley face. Okay. So, on to the next part. And we will not get to an assignment slide here, obviously. Maybe it's not so obvious. But I do want to go ahead and, here in lecture, talk about acid-base titrations, because you guys are going to do them tomorrow. So in General Chemistry 1, you guys did acid-base titrations, but they were strong acids and strong bases. And if you remember way back in with the burettes and stuff, you guys are going to use burettes tomorrow too. But instead of using an indicator, you guys are going to measure the pH as you go. And it's going to make what we call a pH titration curve. So you're not looking for a one color change, you're just getting the pHs as you go. And you should have kind of a pretty curve when you're done. Okay. So you figure we've talked about strong acids, strong bases, weak acids, weak bases, and actually there are 4 combinations. We have strong acid and strong base reacting with each other. Okay. Again, they're titrations, right? So you're going to put something in your burette, you're going to drip it into something in your, whatever, it's a beaker or Erlenmeyer flasks are great for doing that. Okay, so you could have strong acid, strong base. Okay, you could have a weak acid, strong base, a strong acid, weak base. Okay. Or you could have a weak acid and a weak base. So those are your 4 kind of different possibilities. Gen Chem 1, we did the first one. Tomorrow you're going to do the first one, and I think you're going to do the first 2. Tomorrow you're going to do 2 titrations. So we're going to look at a few acid-base reactions, and there'll be one of the 4. Remember, we've talked a lot about can you see, recognize a strong acid when you see one? Hopefully you can. But whatever's reacting acid-base over here, you're actually going to find their counterparts, their conjugates, over on the other side. Okay, so there should be 2 pairs of conjugate acid-base pairs. This is just to kind of remind you, we've talked a lot about conjugate acid-base pairs. You've got to go across the row and find their buddy on the other side that differs by a proton and relative strengths. So HCl, strong acid, NaOH, strong base. What it makes on the product side, acid-base reactions, is it creates a salt. I think we talked about this in Chem 1. Salt. In this case, it's your sodium chloride. It really is salt, right? And water. One-way reaction arrow. So look on either side of the reaction arrow for things that differ by a proton, and you have 2 pairs of conjugate acid-base pairs. 2 sets of conjugate acid-base pairs. Net ionic equation. All right. So on to CH3COOH. Now, you might, does a proton, does this look like it's just itching to come off? Well, it is. Okay, notice actually, there it is without the proton. Okay? So since it's not a strong acid, that must be a weak acid. And actually, sodium hydroxide is a strong base. So we can look on either side of the reaction arrow for things that differ by a proton. You guys have definitely had some practice at this semester. Net ionic equation. So that's your weak acid, strong base. Looks like we still need strong acid, weak base. Okay, you see your strong acid, HCl. You see your weak base, NH3. Two sets of conjugate acid-base pairs. Differ by a proton, and I have the reaction arrow. Net ionic equation. The last one would be both weak. Weak acid, weak base. So if we just use the examples we looked at before. By the way, I think I mentioned this the other day. A lot of time, this is your acetic acid. Acetic acid, and actually this over here, I think we learned it in Gen Chem 1, this is your acetate ion. Anyway, acetic acid is a weak acid. Ammonia is a weak base. Conjugate acid-base pairs differ by a proton. And net ionic equation. Differ by a proton. See, this stuff goes fast. Okay. So, an acid, if you have an acid that's going to react with a base, you can think of it kind of going stepwise. First, what is the acid going to do? It's going to kick off a proton. We call that ionization. Okay. Second, what is the base going to do? It's actually going to attack a water molecule and basically cleave it and release the hydroxide. Okay, the hydrolysis by the base. And then the next thing would be basically that H plus that was released from your acid connects up with the OH minus, or the base accepts that proton, or it connects up with the OH minus that was released by your base, and it makes water. Protonation of OH minus to make water. All right. So we said that if you can take, in this case, an acid-base reaction and break it out into 3 steps, whether they actually happen stepwise or not, okay, then the overall equilibrium constant, K of the reaction, is equal to basically the product, or you multiply the 3 Ks together. Okay, so the 3 Ks multiplied together. So in this case, we have Ka times Kb divided by Kw. Now I'm going to tell on myself here because this might help you guys out. We talked about if you have a conjugate acid-base pair, we said that the Ka and the Kb of them are related by the product is equal to Kw. But these are not conjugate acid-base pairs. These are things that are reacting with each other on the reactant side. The Ka of the acid, whatever it is, times the Kb of the base, okay, divided by Kw is equal to the K of the reaction. But my point here is going to be basically that acid-base reaction that we're talking about is going to favor the product side, okay? It's going to go to that way, to the right, if it has a high K of reaction. And that can only be the case if your Ka or Kb is large. So the Kas of weak acids and the Kbs of weak bases are kind of small. the Ka of a strong acid is large, the Kb of a strong base is large. So that's why actually we're going to focus only on reactions that favor the product side. They have a strong acid or a strong base in them. Okay. The key to the next few slides I want to show you is what does it mean by equal molar quantities. Equal molar quantities means that you have the same number of moles of these two things that are reacting to form products. So basically, if you have the same number of moles of acid and the same number of moles of base, they're going to react with each other. And on the product side, basically they're going to use each other up. Why? Because they're in equal molar concentrations. If you have a strong acid react with a strong base, it's basically they're going to annihilate each other. So it's going to be neutral. No extra anything. Well, if you have equal molar quantities of a weak acid and a strong base, think of it this way. We were just talking about that. That strong base is going to be your limited reactant. Okay, it's going to entirely react. And then on the product side, let me put it this way. On the product side of a weak acid plus a strong base, what's going to drive the pH of that solution, if they're in equal molar quantities, is basically that the B minus that you have created, the conjugate base, that is what is going to drive the pH. pH is driven by that. Because these are all going to be used up. These are consumed. And I'm saying this because actually when we do titrations, that is actually what happens at the equivalence point. If you have a weak acid and a strong base, they're both consumed. And the pH is driven by the conjugate base that was formed. So that was the first two scenarios. The third scenario is what if you have a strong acid and a weak base? We kind of have a similar thing. Okay, so if you have a strong acid and a weak base in equal molar quantities, basically they're going to both be used up. And then what drives the pH is basically the conjugate acid, I'll call it HB, the conjugate acid of that weak base. That's what drives your pH. Okay. And last but not least, the fourth scenario was what if you have weak both? What if you're weak acid and weak base? And we aren't going to be addressing these specifically because it's kind of a mixed bag. The thing is your K of your reaction, it's probably kind of small because your Ka and your Kb are both kind of small. So honestly, the thought of making it just go to the right is not a scenario that it's an equilibrium then. Okay. So like I said, we're not doing the fourth one, but we can definitely do the first three. Makes you want to go out and just learn how that one works, right? So these are terms that we talked about in Chem 1. The titrant is the thing you'll put in your burette. The analyte is the thing that's in your receiving flask, right? And for whatever reason, and tomorrow will be like this too, you're going to put your base. I think if you're given a choice, a lot of times you put your standardized base in your burette, and the thing you're trying to, your analyte is your acid that's in your beaker. The salt is on the product side, I kind of identify what a salt is. Now, the thing we are going to take another look at, or I want you to pay close attention to, is the thing called the equivalence point. There's the equivalence point or the end point, and we are going to say that is actually when you have dripped in the right amount to stoichiometrically use up all of the stuff that you had in your receiving flask. So the equivalence point or end point is basically you have no reactants left. And a few slides ago, remember I said what happens if you're at equal molar quantities, what happens to the chemistry in your beaker. So we'll kind of be revisiting that with this. So equivalence point is very, very, very important, equivalence point. And I think I have a slide coming up in this part 6, that says you need to be able to find where is that tipping point in your chemical reaction, giving that titrant and given that analyte. Where do you have you totally consumed your analyte by dripping in titrant? Okay, so that's the equivalence point. So we can kind of think of the 3 different types of chemistries. There's a chemistry that goes on in your flask before the equivalence point. There's a chemistry that goes on in your flask at the equivalence point. And there's a chemistry that goes on in your flask after the equivalence point. So the 3 regions. So do you see where finding that tipping point can be so important? What titrant do you need to add to reach your equivalence point? Because when I say the chemistry is different, I mean the pH will be different, or the POH, the hydrogen ion concentration will be different. So you've got to know where your equivalence point will be to understand what's going on. So we're going to take the easy way. The first one's going to be the easiest. Okay, strong acid, strong base. So you will be doing, I think this exact same thing. In your burette tomorrow, you're going to have sodium hydroxide. In your flask, you'll have HCl. Okay, and this is a titration curve. So forget all the kind of prettiness and all that. What's important here is, and you could think of this as time, maybe. But actually, instead of time, it's what you're dripping in from your burette. That is, so for instance, here you have 5 mils from your burette, 10 mils from your burette, 20 mils from your burette, 35 mils from your burette, 45 mils from your burette. Burette. That's what's going along the x-axis. This is a titration curve. Along the y-axis is pH. So tomorrow you guys are going to have your little probes in your solution, and you're going to drip in from your burette, and your little probe is going to be knocking out the pH. Now, I think it's kind of like, I don't know if you guys use this in Chem 1, but it's called monitor input, I think. So basically, you'll be dripping in, and you'll basically pause it and say, hey, this is how much I dripped in. So you're going to tell your LabQuest that volume. And it's going to say, well, with that volume, here's this pH. Okay, so that's kind of what we have going on. So does this make sense? It's always good to kind of look at data and say, does this make sense? Well, if I told you what you're dripping into is your acid, it's like a 10 mil aliquot of HCl. Does this make sense that you have very low pHs, which is your acid? You drip, 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 drip at NaOH. And actually, with a strong acid, strong base titration like this, it should come up, it's called I call it kind of an S curve. Do you see the S there? Okay. So that's kind of how that's all going. So let's take a look at those 3 regions. We've got time to look at that. So they took a 10 mil, not 10 mils, you guys tomorrow. They took a 25 milliliter aliquot, I love that word, okay, of HCl that was in a concentration of 0.100 molar, okay. In their burette, which they were dripping in, conveniently, this won't be as convenient for you tomorrow, but the molarity of the NaOH had the same concentration as the molarity of their HCl, which made things pretty easy. So do you see where if in the Erlenmeyer flask we have a 25 milliliter aliquot of 0.1 molar HCl, do you see where we had to drip in 25 milliliters of 0.100 molar NaOH to get our equivalence point? Look where the equivalence point is. Equivalence point. Look where it occurred. What volume of NaOH did you dump in? 25.0 milliliters. That is actually one of the 3 points I said. Chemistry is different before, at, and after. So let's take a look at that. That's kind of what we have going on. Okay. So we have your strong acid, strong base, making your salt and water. All right. So we're going to do, take a look at what happens at 20 milliliters before the equivalence point, 25 milliliters of titrant at the equivalence point. See, I would do this ahead of time, right? What volume is the equivalence point? 25 milliliters. And after the equivalence point, 30 milliliters is after the equivalence point, right? So let's look at what the pH should be in all three regions. So before the equivalence point, basically you have your HCl here, you've added NaOH, and all the NaOH you added has been used up by your HCl. It's before the equivalence point, so what you have is extra HCl left. Okay. So what is the pH? Well, it's driven by the HCl that hasn't reacted yet because you didn't add enough NaOH. Okay, it's before the equivalence point. This is one of these where I think almost you do well if you kind of think of the big picture. Before the equivalence point. So we can actually knock out the pH of that by doing some of the things that we've talked about in this unit. Millimoles of HCl in your 25 milliliter aliquot would look like this. 25 milliliters times use the molarity of the HCl, 0.100 millimoles per 1 milliliter. Okay, so your millimoles is 2.50 millimoles of HCl. So that's what you had to titrate in the first place. Then we can come up with the millimoles of NaOH that you dripped in at that point in the titration. Millimoles at that point in the titration, which was 20.0 milliliters, is this. So we take the volume of NaOH at that point in the titration, 20.0 milliliters. We use the molarity of the NaOH that was in your burette, 0.100 millimoles per 1 milliliter. And so that means we have dripped in 2.00 millimoles of NaOH. Can you see where we're going to run out of NaOH? Yeah, because they react on a one-to-one basis. So the millimoles of HCl that have reacted based upon the limited reactant, which was sodium hydroxide, 2.00 millimoles of sodium hydroxide. We know it's the limited reactant because we're before the equivalence point. Stoichiometry is 1-to-1. That means 2.00 millimoles of HCl have reacted. We're almost done. So if that's what's reacted, we need to subtract that from what we started with to get what's left. So if we take 2.50, what we started with, and from that subtract 2.00, what we used, that will give us the millimoles of HCl that we have in the titration, or at that point in titration, 0.50 millimoles of HCl. Now, here's another tricky part. Here's where you have to we need to divide that by a solution volume, but here's where you need to recognize that we had a 25 milliliter aliquot, and we juiced it with 20 more mils of the sodium hydroxide. So basically, we've got 45 milliliters of solution at that point. So that's how we're going to get to the molarity then. We're going to divide those millimoles by the volume, which is 45.0 milliliters. And if we've kind of stuck with the millimoles, milliliters convention, it just makes it easier. So rounding it to 2 sig figs, the molar concentration of your HCl is 0.011 molar. And we're almost done. So we want pH from that. Well, if we recognize that it's a strong acid, it's going to ionize completely, then the molar concentration of your H plus also is 0.011 molar. And then we can knock out a pH. So of course we know that to get the pH, we take negative log of that molar concentration. So your pH is negative log of 0.011, rounded to 2 sig figs, your pH is 1.95. Which makes sense, you're before the equivalence point. Okay. Well, I think this is good that we got this far. You kind of have a sense for what a titration curve looks like. Tomorrow, I might not do a lot of pre-lab. I might wait to look at the calculations even in class on Friday. We'll just see. I know I don't want to kind of cut you short with your time to do your lab tomorrow, so see you tomorrow.